Today we're going to look at investigating a quadratic function in Vertex form. So let's talk about what a quadratic function is. A quadratic function is a function determined by a second degree polynomial. Okay, so some examples of quadratic functions are y equals x squared and y equals 2 bracket x plus 1 squared plus 3. Today, we're going to look at a quadratic function who has the general form y equals a bracket x minus p squared plus q. And when we take a look at that in particular, we are going to look at the effects of changing variable a, variable p, and variable q. As we make those values different, it's going to have an effect on the graph. Okay? We say, though, that PQ represents the vertex of the parabola. Okay? And generally speaking, we can say that the domain, that's the possible x values, is a set of real numbers. Okay? So this blue curve drawn right here, this right here is a parabola, and it's going to keep on going forever and ever to the right and forever and ever to the left. That's why we can say the domain is all real numbers. Okay? If the parabola opens up, then why it opens up is a is bigger than 0. And if it opens up, then it has a minimum. The minimum is the lowest point on the graph. Okay? And that point is called the vertex. The vertical line that passes through the vertex is called the axis of symmetry. So this is called the axis of symmetry. What's an axis of symmetry? Well, basically it cuts the parabola in half. So if you only knew what one half of the parabola looked like on either half of the line, you could draw the rest of the curve on the other half because you can fold it over the line of symmetry. Okay? Now, we're going to look at the exact same idea, except if a is less than 0, the parabola opens downwards, and it looks something like this right here. And instead of a minimum, there will be a maximum point, and that maximum point is right there. It's still called the vertex, and the vertical line that passes through the vertex is still known as the line of symmetry, and it still cuts it in half. So parabola can either point up or down, and whether it points up or down is completely dependent on the sign of the a value. If it's positive, it points up. If it's negative, it points down. Okay? So what happens if we have the equation y equals x squared plus q, and we change values of q? In other words, we take a look at y equals, we'll take a look at, first of all, a table of values for y equals x squared. We have -3, -2, -1, 0, 1, 2, 3. Okay, those are your x values. And if we take a look at x squared, all we're doing is we're squaring those x values to give us 9, 4, 1, 0, 1, 4, 9. Now, if we have x squared plus 2, then all we're doing is we're adding 2. We're adding 2 to all the y values. 9 becomes 11. 4 becomes 6. 1 becomes 3, 0 becomes 2, and so on, and so on, and so on. So if we have x squared plus 2, we're just adding 2 to all the y values. So if we were to graph this, we would graph the point -3, 11, -2, 6, -1, 3, 0, 2. 1, 3, 2, 6, and 3, 11. Okay? And if we take a look at what that does to the graph, that's where I'll show you what Desmos is. Desmos is a wonderful graphing tool. It's a free app on your calculator. If I take a look at what x squared looks like, then x squared is going to look like that. That's a parabola. That's x squared. But now if I draw x squared plus 2, it looks like this. So if we can take a look at this diagram here, we have the red parabola that represents x squared, and we have the blue parabola, which is represented by x squared plus 2. So if you can look at this graph and think about moving, how would we move from the red graph to the blue graph? We go up 2 points. That's right. So the whole graph moves up 2 spots. That's what happens. That's how we go from the red curve to the blue curve. Okay? Likewise, if we have x squared minus 3, again, we're going to take a look at these values right here, but instead of adding 2 to them, we're going to subtract 3 from them. And if we subtract 3 from them, then we're going to get 6, 1, negative 2, negative 3, negative 2, 1, and 6. So we're subtracting those by 3. Okay? And if you think about what happens to the graph, if it was x squared plus 2, we move the graph up 2. Now, if you think we have x squared minus 3, how do you think we're going to be moving the graph x squared this time? Down 3 would be a very, very wise guess. Let's see if we take a picture of it, if that actually holds. So I'm going to get rid of x squared plus 2 because we don't need it anymore. Now I'm going to type in x squared minus 3. And what we see is that red graph gets moved down 3 units. Exactly as Tyrone said. Okay. All right. Moving on, we can see a summary of this which confirms this. The graph of y equals x squared plus q is the image of the graph y equals x squared after a vertical translation of q units. If q is positive, it moves up. If q is negative, the graph moves down. Okay? So if it's up, it's because that q is positive. If it goes down, it's because q is negative. Okay? Just a summary of what we already talked about. Now, what happens if we change p? So again, we have x and y for y equals x squared. But now what happens if we change it to x minus 2 squared? If it's x minus 2 squared, then what we basically do is, think of it this way. If x was negative 3, then we take negative 3 and subtract 2. And when we do that, we get negative 5. If we take negative 5 and we square it, we get 25. Looking at negative 2 minus 2 is negative 4. Squared is 16. Negative 1 minus 2 is negative 3. Squared is 9. 0 minus 2 is negative 2. Negative 2 squared is 4. 1 minus 2 is negative 1. Squared is 1. 2 minus 2 is 0. Squared is 0. And 3 minus 2 is 1. Squared is 1. So what this is actually going to give you is that if you were to actually graph these points, negative 3, 25, negative 2, 16, is it would actually give you like something that looks like this. It would give you a lot of one piece, and then it would start coming back up. But we could start thinking about, okay, well, 4 would be, what would 4 give us? Looking at the pattern here, what would 4 give us? for a y value? No. Thank you. 5 would give us, yes. 6 would give us, yes, and so on and so on. So it would keep filling in the rest of those points, okay? Now, if we have x plus 3 squared, what happens? Well, think about that. Negative 3 plus 3 is what? Scott, negative 3 plus 3? Squared is? Good. I agree with you. And the rest of them follow. Negative 2 plus 3 is 1. Squared is 1. Negative 1 plus 3 is 2. Squared is 4. And we go on and on and on and on. So what this is actually going to give us is it doesn't actually give us any part of the second part. We're only getting one part of this curve. But that being said, you could probably keep going with some values if you were at all inclined. For example, we could go with negative 4. And if we plugged in negative 4 here, we would get 1. Okay? Negative 5, we would get 4, and so on, and so on, and so on, and so on. Okay? So when we put negative 2 here, what do you think happens to the graph? It's a little tougher to tell, actually. So let's use Desmos to help us figure it out. So again, I've got y equals x squared. Now I'm going to type in x minus 2 quantity squared. What happens to that graph, the red graph, to give us the orange graph? 2 to the right. Yep. And if we take a look at x plus 3 squared, what happens to the red graph there to give us x plus 3 squared? What's it? 3 to the left, right? Yeah. So what we're seeing here is something very important. If we know what the p-value is, understanding that we're using the form x minus p squared. If p is 2, we're moving to the right 2. If p is negative 3, then we're moving to the left 3 units. Okay? That's what it says here. If there's a negative sign here, the graph moves right 2. If it's a positive sign, then the graph moves left that many units. So if it's x plus something in the bracket or x minus something in the bracket, it's going to force the graph to move left or right. Okay? It's going to force the graph to move left or right. Okay? Okay. Now, what if we change a? Now, we change a as in making a, like here we have x squared. A is 1 because it's 1x squared. But what if we change it to 2x squared? Well, order of operations, we still have to square the negative 3 first. So negative 3 squared is still 9. But then we multiply that 9 by 2 and we get 18. So what should we get next here then? If we square negative 2 and then multiply it by 2, what do we get? Good. If we square negative 1 then multiply it by 2, what do we get? No, 2. If we square 0 and then multiply it by 2, what should we get? Good. All those are correct, and we'll just finish it off. So really all we're doing is we're multiplying all the y values by 2. 9 times 2 is 18. 4 times 2 is 8. 1 times 2 is 2. 0 times 2 is still 0. And we're repeating it once more. Okay? And then we're doing the same thing, but now we're multiplying by half. So when we multiply by half, we are going to get some fractions or some decimals, depending on how you wish to represent your stuff. So we multiply 9 by half, we get 4.5. If we multiply 4 by half, we get 2, and so on, and so on, and so on, and so on. Okay? Now, what does that mean when we're taking a look at the actual graph itself? Well, like if I typed in 2x squared, what's the graph going to look like? So what do I do with the red graph to get the black graph? What do I do with the red graph to get the black graph? It gets narrower. Okay. So really what happens is it gets stretched vertically. It would be as if Scott came over to me right now and he grabbed my tops of my arms and he pulled them up, right? The graph is getting stretched vertically. Now, if I typed in 0.5x squared, like it is for the other one, what happens to the graph? It gets wider, and why it gets wider is instead of being stretched, it's being compressed. I don't mind either way of saying it, but they're saying the same thing. When the graph gets narrower, it's because it's being stretched. Narrower isn't really math language. Stretched is more math language. When it becomes wider, it's because it's being compressed. And in both cases, it's vertically. There's a vertical stretch for 2x squared and a vertical compression for 0.5x squared. Okay? And in fact, this is what we can say more accurately. If that a value in front of the x squared is bigger than 1, then we call that a vertical stretch. Okay? But if a is between 0 and 1, it's not stretched, it's compressed. So there's two possibilities there. Either it's bigger than 1 and it's a stretch, and a vertical stretch at that, or it's between 0 and 1, and if it's that, then it's a compression, a vertical compression. Okay? So stretch and compression are the mathematical terms that we use to represent those situations. She's away. Now, what happens if these are negative now? If these are negative, this is really simple, okay? Because we're going to get the exact same numbers we got last time, but when we multiply by a negative, it obviously changes the sign. And all those y values are positive, so the y values become negative. And this is what we said right off the hop of this lesson. We said that if a is positive, the graph is going to point up, and if a is negative, the graph is going to point down. So again, to represent that here, I'm going to show you what negative 2x squared would look like. Negative 2x squared is going to look like this. It's going to look the exact same that 2x squared looked like, but instead of pointing up like x squared, it's going to be going downwards. Its vertex is still at the origin, 0, 0, but it's going to shoot down from the left and to the right. And if I draw negative 0.5x squared, we're going to see the exact same thing. We're going to see that the graph becomes wider because it's being compressed. But the only other thing that's also true is, instead of pointing up, it's pointing down. Okay? So the sign on A tells you whether the graph's pointing up or down. And the value of A tells you if a stretch or a compression has been made. And if A is 1 or negative 1, then there's no stretch or compression. It's only if A is bigger than 1 or between 0 and 1. Okay, so, and here it kind of says that, but it says it a little differently. It says if it's pointing down and a is less than -1, so it could be -2, for example, then it's a vertical stretch. But if a is between -1 and 0, like -0.5, then it's a vertical compression. Okay. Now, if we have a graph of x squared and we have another graph, we can determine what P and Q are as well as A is. So let me show you something first before we go there. Let me show you something here. And to show you this, I'm actually going to go on a separate piece of paper here. And I'm just going to insert a graph here just so you know. I want to show you how to graph x squared. And I'm talking about plain old x squared, not anything that happens to it. Okay, let's look at plain old x squared here. Plain old x squared should be easier for you to draw than, like, you should be able to get comfortable with graphing this almost by memory. Okay, plain old x squared is always going to have a 0, 0 point. Okay, plain old x squared, then we have to ask ourselves, what's 1 squared? 1. So there's going to be a point at 1, 1. What's -1 squared? 1. So there's going to be a point right here. What's 2 squared? What's -2 squared? Also 4. What's 3 squared? And -3 squared will give us the same thing. So these are the points that are always on the graph y equals x squared. Always. Okay? You can always make those points. Here's the interesting thing about these points too. If you look at the vertical differences, and this is important for identifying A, if you're looking at a graph of two functions on the same set of axes, the difference between these 2 points is 1 unit. The difference between these 2 points is 3 units. The difference between these 2 points is 5 units. 1, 3, and 5 are all what? What kind of numbers? Odd. What do you think the difference is going to be for the next two? If we follow this pattern, 1, 3, 5, 7. And you're right, it is. Because it'd be 16, and 16 minus 9 is 7. That's important when you're looking to graph it, because why I'm saying that is this. If we go back to this lesson here, we can see that the differences here are 1, then 3, and we can't really see 5 here because it doesn't go up that high. But if we take a look at the second one, we see that it's 1, and then we see that it's 3. Because the vertical differences of the dotted graph here are 1 and 3, just like the solid graph, that tells me for sure that A is 1. A is not changed for the dotted graph. But here's what we do know. The graph gets moved to the left 1 and up 1, 2, 3 units. Because it gets moved to the left 1, that tells us that P is going to be -1. Okay? And because it goes up 3 units, Q is 3. So the equation would be y equals x plus 1 squared plus 3. And the tricky part about this is, we know because it's x minus p in here, so I know it's x plus 1, but it's x minus p. So if you have minus -1, that makes +1. So this is what the dotted function would be. It would be a value of 1, x plus 1 squared plus 3. Because the way to get the dotted graph is just to move the curve over 1 spot to the left and 3 units up. Okay? So that's how we do this. We have to look to see if there is going to be an a value other than 1. And that's why I showed you that thing. Yeah, it would be a 2. It would be a 2. And what it would be is those differences, instead of being 1, 3, and 5, would be 2, 6, and 10. The differences would be 2, 6, and 10. That's right. Like, so if it was 3, 9, and 15, then A would be 3. Okay? So it's whatever, so you compare what the differences are to what they should be, and whatever factor they're off by tells you the value of A. Okay? And of course, if the graph is pointing down, A is negative. Okay? What else do we have? Okay, here's one right here. Here's one right here. We are going to determine the equation of this graph of a quadratic function. So from this graph right here, we can go ahead and figure out A, P, and Q. Now, P and Q are going to be really obvious because the vertex is at 3, 2, right? 3, 2 is the vertex. So the equation is y equals A bracket x minus P squared plus Q. So the function is going to be x minus 3 squared plus 2. And then all we have to do is we have to figure out what A is. Okay? Now we could figure out A by using those differences that we talked about. Okay? So for example, what I can see on this graph here is we go over 2 units. Okay? Now I'm going to go back to this thing right here. If we went over 2 units here, how much should it go up by normally? 1, and then, so over 2 units means a total vertical displacement of 4, right? If at the standard x squared, we should be going over 2 and up 4. 1 and 3 makes 4. So if we go back here, we go over 2, and how much do we go up by? 2. So think about that. We're supposed to go up 4, but we only go up 2. So what would A be? 1/2. Very good. So A is a half. Da, 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 da. There we go. So A is a half because it's supposed to, in 2 jumps horizontally, it should go up 1 and then 3 for a total of 4, but it only goes up half of that, so A is a half. So just by looking at this graph, we're able to figure out what A is, what P is, and what Q is. Okay? It's pretty cool. All right. Okay, here we go. And this kind of goes to what I was saying. The pattern in the first differences of a quadratic function can be used to graph the function. Here is a table of values in the first differences. So what it does is it finds the differences between each of these values. And you're going to see we get the exact same thing as we got before. We get 1, 3, 5, and 7, just like we did. And here we get -7, -5, -3, -1. Okay? And it's the same kind of approach that we just did on that other piece of paper. It talks about the 1, the 3, the 5, the 7, the 1, the 3, the 5, the 7, just like we did on that other graph that I drew. Okay? So these can help us, especially if we're looking at a curve and we're needing to come up with the A value, just like we did in the last question. All right? So these first differences can help us. Because if the first differences are not these, then that means that A is not 1. A is something other than 1. Okay? So here, yeah, we already talked about this, but just for clarity here, again, we're moving from the vertex. we're moving over 1, up 1, over 1, up 3, over 1, up 5, over 1, up 7. If we kept going one more, we'd go over 1, up what? 9. That's right. And we do that in both directions. Okay, we do that in both directions. So here's an example. It gives us an equation here, and we need to answer all these. In which way is it opening? What's the vertex? What's the equation of the axis of symmetry? What are the intercepts? And what is the domain and range of the function? And then sketch the graph. So we'll start off with the direction of opening. Is this opening up or down? Why? Giddy up. Down because A is negative. That's brilliant. Good. Okay? Now, what's the vertex? Be careful. What's the vertex? Vertex is going to come from your P and Q values. The trick is to always take the opposite sign. Whatever this is, take the opposite sign. So it's going to be -2, but then you don't take anything different for the Q value. So the vertex is going to be -2, -3. So you take the opposite sign for P, but Q is -3, and we take that -3. Then we have the equation of the axis of symmetry. That's always going to be x equals. It's always going to be x equals, and what it's equal to is this number right here, your P value. So it's going to be x equals -2. But don't tell me just -2, because if you tell me just -2, you're not right. It's an equation of a vertical line. Any vertical line is always in the form x equals a number. So you have to put the x equals in it. So it's x equals -2. What are the intercepts? This is the cool thing. Here's the thing. Let's picture this for a second here. I'm just going to draw a very, very loose diagram of what this would be. -2, -3 would live down here. Now, which direction are we moving in, Tyrone? Up or down? So if we talk about the intercepts, we're going to get something that looks something like that. Okay, that's a very loose sketch. But that's important for a very important reason. When we talk about intercepts, we're talking about where does this graph hit the x-axis and where does this graph hit the y-axis. So Scott, how many times does this graph hit the x-axis? No. This is the x-axis. How many times does the graph hit the x-axis? It doesn't hit the x-axis. It can hit the x-axis, it absolutely can, but this one won't. As a matter of fact, the only axis it hits is the y-axis, and it'll only ever hit it once. It can never hit it twice, okay? Hits it once. So where does it hit it? Well, if you ever want to find out what an intercept is, you plug in 0 for the other variable. And when we're talking about quadratics, the y-intercept is always easy to find. The x-intercept is always trickier to find. So here's what we're going to do. We're going to plug in x equals 0 to find out what y is. So that would be y equals -2, 0 plus 2 squared minus 3. So y equals -2. This will be 2 squared in the bracket minus 3. Y equals 2 squared is 4 times -2 is -8. Take away 3. Y equals -11. So the y-intercept is -11. The x-intercepts, there's none. And we should say there's none. Because there's a difference between leaving that blank and saying there's none. If you say there's none, it's clear that you've thought about it and you've decided that there's no x-intercepts. Okay, but there's only one y-intercept and it would be -11. Now it asks us, what is the domain or range of this function? Well, the domain, if you remember from the very first page of these notes, is all real numbers. And we can write that as -infinity to infinity. All real numbers can be represented by the domain. X can be anything we want it to be. The range is a little bit of a different story. Does this graph have a maximum or a minimum? Maximum. What's the maximum y value? -3. That's the maximum. So, and it goes all the way down below that. So how do we represent that? Well, we would say it'd be negative. Oopsies, I kind of messed that up already. We're going to go from -infinity to -3. But you see, here's the difference, okay? Here's the difference. The graph can never equal infinity because infinity is not a number, it's a concept. But the graph hits -3. So because it's equal to -3, we're going to put a square bracket for -3. And we have to do that when we write our domain and range. If the graph actually touches that value, then we use a square bracket to represent that part of the interval. But if it doesn't, or we're talking about infinity, we always have to use round brackets. Okay? But in this class, we'll always be talking about the domain of a quadratic function going from -infinity to infinity. The range will be dependent on whether there's a minimum or a maximum. Another example. The equation of the axis of symmetry of the graph of a quadratic function is x equals 1, rather x equals -1, my bad. The graph passes through the points 0, 3, and -3, 9. Determine an equation for the function. This question is pretty tricky. I think this is about it, though. We're almost at the end here. So what does this mean? Remember a little while ago, I said that the axis of symmetry is found by using which letter from the equation? A, P, or Q? A, P, or Q? P, yeah. So this right here is a gimme. It tells us that P is -1. Okay? It tells us that P is -1. That is, the x-coordinate of the vertex is -1. Now, we also know that the graph passes through 0, 3 and -3, 9. Now, this is going to remind you a little bit of what we did in the first unit when we talked about arithmetic sequences and series, because we came up with an equation with two unknowns. It's going to be the same thing here, because we know the vertex form of a parabola, any parabola, is y equals a bracket x minus p squared plus q. And we know in this particular question, p is -1, so it's going to be y equals a bracket x plus 1 squared plus q, and we know that's always going to be true. What we don't know is a, and we don't know q, but we can plug in points a and b separately into this expression, and they will give us equations. So let's do that. Let's plug in 0, 3. So 3 equals a bracket 0 plus 1 squared plus q. 3 equals, that's going to give us 1 squared, which is 1. So that's just a plus q. So we know that a plus q is equal to 3. Now, we have no idea what a and q are, but we know that if we add them together, it gives us 3. And we got that by just substituting this point here into that equation there. And we're going to do the exact same thing with point B. So we're going to get 9, that's y, equals a bracket x is -3 plus 1 squared plus q. So that's 9 equals, now -3 plus 1 is what, Scott? -2. If we square -2, Scott, what do we get? Giddy up. We get 4a plus q. Now, the cool thing about this is that these equations are going to be, they're very friendly. They're very easy to work with here, because if we take these two equations and we subtract them, We're going to find out what A is. So I'm just going to put them on top of one another so we can subtract them. If I subtract them, I get 6 equals, the Q's cancel each other out. I've got 4A minus A, which is 3A, which is really nice and simple. So what's A? It's 2. A is 2. And if we go back to this pretty straightforward equation, we said that we don't know what A and Q are, but we do know if we add them together, we get 3. Well, if A is 2, what must Q be? 1. So we go back to this equation up here, and we replace A with 2 and Q with 1. So that's going to be y equals A, which is 2, bracket x plus 1 squared plus 1. That would be the equation of this quadratic function. So what we're doing in this question is we are going back to grade 10 when you studied linear systems and you found solutions to 2 equations with 2 variables, and that's what we did here. We came up with 2 equations with 2 variables. Both are highlighted blue. And then all we did was straight up subtracted those equations, because it worked out really nicely, because in both cases, Q had no coefficient. So we're able to subtract them really nicely and find that A was 2. And then using the fact that they added together to give us 3, it followed really nicely that A is 1, or rather Q is 1. Now this question was a pretty involved question. There's no two ways about that, okay? But we're not using any math that we haven't already used in this semester, and you learned in grade 10 as well, okay? It just meant that you had to kind of know where to go and then just follow it through, okay? So here we want to try and figure out how many x-intercepts there are. So you remember how we kind of did that? We drew the picture and we took stock of where the vertex was and whether it pointed up or down. So really what you want to know is this. Does the vertex land above or below the x-axis? And then does it point up or down? Because that's going to tell you whether there's 0 x-intercepts, 1 x-intercept, or 2 x-intercepts. What is the vertex of this first equation here? One and 8, so that's like way up here. And if we're and which direction are we going, up or down? So how many x-intercepts would there be? Good. You got it right. Good. Cool. Okay, next one. What's the vertex of this quadratic function? And we're pointing up or down. So how many x-intercepts will there be? Correct. What would the vertex of the third quadratic function be? Two and 0. 2 and 0. And it's pointing up or down? How many x-intercepts are there going to be? It would just be 1, because the vertex, it would, very loosely, it would look like this. It'd be right on the x-axis. So for that reason, there is exactly 1 x-intercept there. That's correct. Moving on, we got 3x squared minus 7. What is the vertex? Correct, and it's pointing. So that means there's. Do you believe that, Scott? Do you think there's two? You should. There is two. Because it's below the x-axis and it's pointing up. What's the vertex of the next one? And it's pointing. How many x-intercepts? Yep. And last but not least, what is the vertex? And we're pointing. So there's. You bet. So just by looking at the graph, without even graphing it, knowing what the vertex is, whether it's above or below the x-axis, and whether it's pointing up or down, you can figure out whether there's 0, 1, or 2 x-intercepts. And you're going to get questions like that in your homework. But understand this. The question doesn't ask you for what the x-intercepts are. It asks you how many there is. And the answer can be none, 1, or 2. Okay? Lowest point 2 meters above the center of the ropes. Determine equation. What assumptions are made? Okay, so here we go. A 12-meter long suspension bridge is made up with ropes and logs. The rope forms a parabola with its lowest point 2 meters above the center of the bridge. The ropes are attached 6.5 meters above the bridge. Determine an equation to model this parabola. What assumptions are made? Let me tell you this. We can all draw this differently. And we can all be correct as long as we follow through on this. So we have to draw this with the idea that there is a Cartesian plane somewhere. Okay? I would do this. I would draw something like this. I know that's so ugly. Let me see if I can do better than that. I'm just going to leave it like that because this is longer. Good enough. Okay. We need to label some points here. Most notably, the middle. We know the middle is going to be the point 0, 2. And 2 because it's 2 meters above the center of the bridge. Okay? Now, on the far right, understanding that this is a 12-meter long suspension bridge, I'm going to have points that are 6, and it says 6.5 meters above the bridge is the height on the end. So that's 6 and 6.5. And this would be -6 and 6.5. So we have our points. And these points will help us figure out what the equation is. The most important point there to help us out is the 0, 2. The 0, 2 tells us what the vertex is. Okay? It tells us what the vertex is. So from just the point 0, 2, we know that the equation's y equals a, bracket. It's x minus 0. Now, x minus 0 is just x. So it's just x squared plus q, so that's plus 2. So what we have to do in order to figure out this equation is we have to figure out the value of a. We have to know what a is equal to. And to figure out what a is equal to, all we have to do is use one of these 2 points. It doesn't matter which one we pick. And we have to plug it in for x and y and figure out what a is. In my world, it's always easier to use positives if positives exist. So for that reason, I'm going to use the positive point. Okay? So you're plugging that in for x and y and solving for a. So this is going to be 6.5. This is going to be 6 squared plus 2. 6 squared is 36 plus 2. We do have to follow order of operations. We have to bring the 2 over to the other side, so that's 4.5. And then to figure out what a is equal to, you're going to love this. It works out beautifully. If you divide 4.5 by 36, you're going to get a nice decimal answer, because basically here's this. 4.5 goes into 36 exactly 8 times. So this fraction, although it looks goofy because there's a decimal in the numerator, it actually works out really nicely to 1/8. So a is 1/8. And with that, we then know that the equation is y equals 1/8 x squared plus 2. And now, is that it? Yeah, that's it. Okay. We could ask a follow-up question where we have to use this equation, but that's how we go ahead and figure this out. Okay. We have to algebraically solve for the value of a, and then once we do, plug it back into this equation right here. And that gives us an equation that models the parabola. Now, understand this. The assumption that we would make is that the rope is perfectly tight enough that both sides of it are symmetric, and also they form the shape of a parabola. And lots of times, to make our lives easier, we do use a simplistic model like that, but in the real world, things aren't always as simple as you might want them to be. Your homework for this is pages 157 to 161, numbers 1 to 23.